I, Deb Neer, you're right there. You know the difference between dirt and soil, right? Yeah. Dirt is just soil out of place. So anyway, it's an old dirty joke. And Allison has to put up with bad jokes like that all the time with working with me as well. But good afternoon. I'm glad everyone is here this afternoon. And I get to kick off and tell you a little bit about what this series is attempting to do or will do this semester. Allison and Joya and others have put in lots of work to bring in some good speakers. And our kickoff speaker this afternoon is Eric with some really intriguing information around the tying of energy and food. So it's going to be a very, very interesting opportunity to listen to Eric and then others as the season goes on. What is the Food Systems Initiative? The University of Vermont 3.5 years ago decided to have 3 focal areas for work on this campus, and one of them was food systems. And the one thing that really garnered a lot of attention, because this was reviewed by the faculty and by external presidents of other institutions, and it all came around and there was a competition among 7 different possible initiatives, and the food systems was rated #1 because it tied scholarship and teaching as well as what's going on in the state, both from the agency side of things, but from all the farmers in this state and the local farmers markets, and how does the university tie itself more closely to both the state in these areas by bringing our scholarship and our teaching to impact that across the state. So this initiative is like the other 2 initiatives, but we have one component that's very critically and equally important, and that is the outreach component. So we have the research, the teaching, and the outreach. All of these initiatives are transdisciplinary. We're always coming up with new words. You may have heard of multidisciplinary. Well, this is transdisciplinary. And basically what it is trying to get people coming together to solve problems from different perspectives, because the problems, as we all know, are very complex, and the era of just trying to solve them within our own discipline is very, very difficult, and you need to bring people together to interact to help solve those problems. We also promote a community-focused food system. And some folks in the state will use a community-based food system. I often use community-focused because a particular farm or farmer activity may not be based in that community, but may have an impact on that community and may be selected by that community to be part of their food system because of its impact or lack of impact in some other location in the state or the world. We work with partners across the state, Farm to Plate, nonprofits, and others, NOFA. We have a role in developing models and offering learning opportunities to strengthen the state's food system, and that's our land-grant mission. The University of Vermont is something called the Land Grant University, and there are 50 of them across the country that were established in 1862 or shortly thereafter. There have been another 50 or so added through the decades for historically black-serving institutions and Native American institutions. But part of that land grant status is you work on problems and you bring your knowledge to solve those problems into the communities. And we see the UVM campus food system as a learning laboratory, and especially as I talk a little bit later about Farm to Plate and the new the RFP the request for proposal for a new dining service, or I shouldn't say a new dining, the next vendor for the dining service. It may be Sodexo, it may be someone else as we go through this request for proposal system. So it's an opportunity. How can the university use its own dining services, its own campus, to interact with Burlington and other communities, to be a model of how we meet our values and how do we move forward as a society in dealing with food and energy and all the things related to ourselves. We're doing this in concert with the Office of Sustainability. And Joya is sitting in the back row there as the head of the Office of Sustainability. And I'm going to read her statement on what that is, because I don't know that as well as the food systems one. But it's to foster sustainable development and promote environmental responsibility at the University of Vermont by strategically bridging the academic activities of teaching, research, and outreach with the operations of the university. So Joya works in concert with the Clean Energy Fund, which is a student-funded organization. There's a $10 fee that all the students pay that go into this Clean Energy Fund, and Joya helps manage that. And between the Office of Sustainability, the Food Systems Initiative, and the Clean Energy Fund, that's what brings all of us together here today and for the seminar series as we go through this spring semester. So in projects that the Clean Energy Fund pursues, they want to recognize and pursue links between food and energy systems in this seminar. And they fund things such as, or look at funding things such as the solar panels at the Miller Farm, supporting student-led research projects to install renewable energy heated greenhouses at Slade and at the University Hort Farm. So the Clean Energy Fund is an undergraduate-driven entity and funding mechanism to make us more energy sustainable. And so the tying of food, which uses a tremendous amount of energy in this country, and in the preparation and storage of it, it's a very apropos combination. So what's going on at UVM? Just two highlights right now. One is the Real Food Challenge. That's made up of students and faculty and staff and Sodexo employees. And that says we should shift our food purchases and our procurement to real food, or at least 20% of it being inventoried as real food by 2020. And what is real food? It's defined as being local, sustainable, fair trade, and humane. And UVM was the 5th institution in the country to sign the Real Food Challenge back in March of 2012. It is a student-led initiative to transform the university dining halls across the country. So it's a working group, as I said, of students, faculty, and staff, and I believe their next meeting is this afternoon at 6 o'clock or 5:30. So if you're interested in that, you might want to drop in and visit. We also have a second item. There's the Sodexo contract is ending its 10-year run in July of 2015. And as part of due diligence, we are putting together a new request for proposal, of which that will be going out into the marketplace for any food service organization that services universities will be able to apply for. And so it's important that as we go through these seminars this spring, if you have thoughts about, you can see a paper up there, if you see thoughts about what you think our food system should be like, or what you like about it currently, or what you would like to see changed, there'll be notes during the question and answer section as well, but if you have an idea that doesn't seem to come up and doesn't seem to fit, feel free to write it down, because we're going to be collecting those, and the seminar will be providing those to the committee, the dining contract committee, that will be putting together the request for proposal. We want that request to show our values and balance costs and its impact on the environment, and so your input today and in future seminars is very, very important. So with that, did I miss any critical components, Allison? If not, then I'll turn it back to Allison to introduce Eric.
Thanks, Doug. So next up we have Eric Garza, and our goal here is to have Eric sort of set the stage for discussions today and for our discussions the rest of the semester as we understand the interactions between our food and energy systems at the institutional level and at other scales as well. Just as doing some preparation for today's talk and talking to Eric, it's really critical that we understand the complexities of these interactions, because sometimes we're faced with appealing, but what may turn out to be sort of false solutions around synergies, and we end up seeing that there can be trade-offs between different efforts in energy and food sustainability. So it's really critical that we understand these issues from an empirical base and the evidence that we can gather from empirical study, and also use that evidence and be guided by our values, like as Doug was mentioning before, as we move forward with decisions at the institutional level. So Eric Garza is a lecturer in the Rubenstein School of Environment and Natural Resources here at UVM. He's also the founder and owner of a small consulting company called Aesthetica. Eric holds a PhD in natural resources from UVM, and as well as master's degrees in environmental science and public affairs from Indiana University. and a master's in biology and chemistry from Purdue University. He teaches courses in energy and food systems. This semester, he's teaching complexity in food systems. This past fall, he taught a course called Mapping the UVM Food System, in which UVM students tracked and documented different food purchase and procurement amounts at different dining halls across the campus so that we could have an understanding of what the flow is looking like for different products through campus. During his time as a PhD student at UVM, he was a founding chair of the Clean Energy Fund, which Doug was mentioning, and also served on the Socially Responsible Investing Working Group for a time. He works with a range of partners, studying energy intensity of food production, focusing particularly on local food systems. So I'll turn it over to Eric.
Okay, thank you very much. I'll give another thanks to the Clean Energy Fund and Office of Sustainability for organizing this, and especially to the Clean Energy Fund for making some funds available to bring some innovative speakers in for the rest of the semester. So what I'm going to do with this talk is I'm going to, as Allison said, I'm going to go over some of the data on energy intensity of food systems, particularly at the national level here in the US, but also with some of the energy audits that I've done for small local farms here in Vermont, kind of as a juxtaposition. And the talk that I'm going to give is going to be around 20 minutes or so, and then we'll open everything up for questions, and I hope that we can come up with a pretty lively, informative discussion about some of the facts that I'll put forward. And and I think that'll be a good afternoon. So what I'm going to start with, though, actually is a little bit of audience participation to try to set the stage for kind of one of the reasons why I'm so interested in studying energy use in food systems. So the first question that the big question I want to ask: how many people in the audience have noticed that food prices have been trending upwards? Most people. Not too surprising. And your beliefs are well-founded. This is a graph from International Monetary Fund looking at food price indices. This is actually global data. This is not just US data. And prior to the year 2000, it would bounce around a little bit here and there. But since about 2000, really since about the latter part of 1998, we've seen a pretty steady upward trend in food prices around the world. And not only have we seen a general upward trend, we've also seen a pretty radical increase in the volatility of food prices. And those of you who've been watching the news for the last few years have probably noticed that when you see radical swings in food prices, you oftentimes see food riots around the world. Because here in the United States, we only spend 8 to 10% of our income on food. But in other parts of the world, people might be spending 20%, 30% or more of their income on food. So a swing of food prices that doubles the price of some important commodity like corn or soybeans is going to make a huge, huge impact on the lives of people in other places. So what does this have to do with energy? And the answer is that when you look at an index from the International Monetary Fund of fuel prices, you see the same general trend around the world as you see with food prices. You see a general increase in energy prices after about the year 2000, and the pattern of volatility that we saw in food prices is mimicked by, I shouldn't say mimic, but is similar to the pattern of volatility that we see with energy prices. There's a reason for this relationship, and the reason, and Doug and Allison both kind of alluded to this already, is that producing food in the industrialized food system that we have today, both in the United States, but also around the world, is a very, very energy-intensive endeavor. And when the production of food is such an energy-intensive endeavor, it shouldn't surprise anyone too much when you start seeing the price of food tracking the price of energy, which is a key input into its production process. And I'm not necessarily saying that energy prices are the only thing that matter in determining food prices, because of course they're not. But I'll present some data suggesting further on that they're going to be, we would expect them to be a pretty big portion of that. And one of the ways that I find useful to look at the energy intensity of food systems is through an idea called return on investment. Return on investment is something that's used in a wide variety of different circles. Economists use it, people in finance use it. Those of us who study the viability of different sorts of fuels, particularly biofuels, also use it. Return on investment is a very generalizable idea. A lot of it revolves around looking at the output of a production process and just comparing that output to the inputs that are required into that production process to facilitate the production of the output. What we're interested in here is a more specific application of return on investment that is called energy return on investment. Here we're looking at some sort of an energetic output. In this case, the energy value of the food produced by a food system. And we're comparing that to two types of energy inputs. One of these is direct energy. The other is indirect energy. And the easiest way to explain what these two mean is probably with an example. If I have a small farm, and if I were to look at this from a systems perspective and define my system's boundary as the property boundary of that farm, the direct energy represents fuels that are purchased by the farmer and that are burned and used within that system boundary. Whereas the indirect energy represents fuels that are burned in support of that farmer's operation, but are not necessarily burned within that system boundary. So, more practical example, a farmer buys diesel to run his tractor. The diesel fuel would represent direct energy because that diesel fuel is burned on the farm. The energy that is required to manufacture that tractor and to deliver it and to maintain it, most of that energy is used off-site at factories that manufacture the parts, at the place where the tractor is put together. All of that energy is thought of as embodied in that tractor when it crosses the system boundary onto that farm where it's used. So the direct energy is used on-site. Indirect energy is used off-site to produce things that are necessary for that system's operation. So why don't we go ahead and dive right in. So a lot of the, actually, you know what, I'm going to go back and point out one other thing. So with our industrial food system, what we are basically doing is we are taking energy sources that we cannot eat, things like gasoline, diesel, natural gas, a range of different fuels that can generate electricity, and we're turning all of those energy sources into food that we can eat. And there's a calorie value to all those different industrial fuels. There's also a calorie value to food. So with our industrial food system, we are using all these sorts of different processes to take that fossil fuel that we can't eat and that can't nourish us and turn it into something that can. So that's kind of the energetics, kind of a basic energetic understanding of what the food system does. And we can look at the results of that process. We can start with this graph here. What this graph is showing is the number of input kilocalories of energy, mostly fossil-fueled energy, that it takes to deliver 1 kilocalorie of food. And the LA there is loss adjusted. So what this does is it doesn't look at total food that's available. It looks at the amount of food that people actually eat. So I'm correcting total food production for the 35 to 45% of the food in the United States that ends up wasted or spoils before anybody actually eats it. So input kilocalories are inputs, the food calories are the outputs. So this is a flipped version of the return on investment equation that I just shown, because in the case of the United States, we put in a lot more kilocalories as inputs than we get back as food. So if I left it as output over input, we'd be dealing with really, really small decimal numbers, which are challenging for people to interpret and relate to. So by flipping it, we can talk in big whole numbers, and it's easier to relate to. So this is U.S. Department of Agriculture data for the year 2002, breaking our food system down into roughly 4 categories. At the bottom, we have producers, agriculture, that uses a little under 2 units of input energy to deliver each calorie of food. The two bluish tinged blocks are thought of as the processing stage of the food system, so food processors and also the packaging stage. And then above them, you have the 3 green shaded areas represent kind of the distribution side of things. So we're looking at freight, which is long distance transport by barge, by airplane, by 18-wheeler. And then at the very top, well, there's freight. Sales represents wholesalers like Black River Produce, people that are distributors of food. And then the retail sales are places like grocery stores, so like the city markets, Hannaford's, Price Choppers. And then the other big chunk of the distribution side is food service enterprises, so restaurants and catering services. And you can see that the distribution side is the largest chunk of this pie so far. And then, of course, at the very top, we have the household side of energy use. And household represents the electricity that's used to power people's refrigerators and freezers, the heat energy used for cooking, and also the energy it takes to drive people to and from restaurants, to and from grocery stores. So the household energy use is a pretty sizable chunk as well. And if people have questions about the particulars of this, we can certainly revisit this later on. Another point that I wanted to make, though, right now we stand in 2002 at around 13 or 14 input calories for every output calorie of food. It's important to realize that the way that the U.S. Department of Agriculture did this study, they actually left a lot of things out. They didn't necessarily count everything in the food system. Some of the things that they left out include the energy that's needed to power wastewater treatment and waste disposal in general, so solid waste, so food waste, as well as all the consumable plastic containers and such that are created from our food system. They didn't analyze that, so that's not in here. They also leave out the governance of the food system. So, the USDA, Food and Drug Administration, Center for Disease Control and Transmission to a degree. All the energy that it takes to make and enforce regulations, to do inspections, all the different extension officers who drive all around states supporting different elements of the food system. All of that energy that supports that is not included in here. And then the last piece that they did not include, this is all input-output data, which comes from economic tables published by the Bureau of Economic Analysis. So the analysis that they did stops at the political boundaries of the United States. It does not include the energy that it takes to produce or process food that is made in other countries that is imported into the United States. It also doesn't include the energy used to manufacture equipment, machinery, or other things that are made outside of the United States and then imported in. This draws a boundary at a political boundary. So all the stuff that we import, the embodied energy in that stuff is not counted in this. So usually when people ask me what the total is for the U.S. food system, the best educated guess that I can come up with is that it takes somewhere in the range of probably 15 to 20 kilocalories of energy input to deliver 1 calorie of food that someone actually eats in the U.S. So if we turn that into a return on investment, we're talking about 1 unit of output over 20 units of input. So, a pretty big energy sink as far as that goes, although we're turning energy that we can't eat into energy that we can. And the data that I showed just there was from 2002, as one would probably guess. The energy intensity of the food system is not a static number. It's something that changes over time as a function of our level of development and also the types of strategies that we use to produce food. So this is a graph where I've reconstructed a longer-term time series of data looking at the energy inputs relative to loss-adjusted food outputs of the US food system. And you can see that back around 1910, the input over output was a little over about 1.5. So it was a lot closer to breaking even in terms of the input to output ratio than it is today. And the radical increase stems from a lot of different things, but a couple of the big things that drive this is the fact that we have, on the one hand, largely mechanized our food system. We have replaced human labor, which is fairly energy efficient relative, per unit of work done, with machines, which can do a lot more work more cheaply, but at the same time, they are a lot more energy intensive per unit of work done. The other big thing is that we have come to rely a lot more heavily on foods that are processed and foods that move through, commercialized distribution channels. And that adds a lot of energy to the total inputs. What this graph does is it breaks 2002 data from the US Department of Agriculture down as a function of different types of foods. So meat, seafood, poultry, eggs, dairy, fruits and vegetables I had to lump together because of the peculiar way that USDA reports statistics on those, and then grain. And it's important to realize, I guess, first of all, that I don't have all the same categories here as I did in the graph a couple before because the USDA did not break down energy use in food service sector or in household energy use down by individual types of food. So those are not in this picture, so this is an underestimate of the total. But you can get a sense for general trends based on the types of foods that are used. The other thing to realize here is that that not all food is created equal, effectively. Some foods are more energy intensive on average to produce than others. The other thing that you need to realize is that all of these represent averages. So not every single meat operation is going to necessarily be this energy intensive. Some of them will be much more energy intensive. Some of them will be much less energy intensive. And the same goes with all of these different types of foods. And we'll see that most explicitly when we look at some of the energy audits that I've done. So these are looking at I collect data in a different way rather than looking at distribution versus agriculture, et cetera. I will break down, I do on-farm energy audits by the energy value of labor, the energy value of fuel, which usually includes things like electricity, diesel, gasoline, natural gas, propane, and then the embodied energy of machinery, the embodied energy of buildings, and then the large category of farm inputs, which can include things like pesticides, the embodied energy of pesticides, embodied energy of fertilizers, embodied energy of consumable goods, and a wide range of other things. All kinds of soil amendments are stuck in there. The embodied energy of them gets stuck into there. And so as we look at some of these different types of farms, we had a pasture dairy diversified farm that offers a range of different fruits or a range of different vegetables as well as some meats and bread. Vegetable CSA, which is certified organic, pastured lamb operation, another vegetable farm which is certified organic, a pastured meat operation which does mostly pork but some beef and a small amount of eggs, and then of course a maple sugaring operation. You can see right away that there's a huge array of energy intensities that you can see on these relatively small farms that operate at the local level and distribute their food at a local level, which illustrates the fact that the management style of a farm makes a huge difference in how energy intensive it will be. The kind of products that a farmer decides to produce is going to make a huge difference in what the energy intensity of their farm is going to be. And then the distribution method that they choose is going to make a huge difference in what in the energy intensity of their operation. So some of these do direct marketing. They sell direct to consumers at farmers markets. Some of them do CSAs. Some of them will have wholesale accounts, so they'll deliver to Black River Produce, or they'll deliver to restaurants, or they'll deliver to City Market. So and some of these will do a wide array or multiple of these distribution methods. So, all of those different things factor into how energy intensive this particular operation is going to end up being. Which, the nice thing about that is that because all of those different factors matter, it gives us a lot of leverage if we wanted to, help a small farm become a lot more energy efficient than it is relative to, the food value, the energy value of the food that it produces. We have a lot of wiggle room. And a lot of the small farms that I work with have never necessarily had an energy audit before. So for a lot of these farms, there's a lot of low-hanging fruit that you can use to help get their energy intensities downwards. And I think at that point, I will open it up to questions. And if anybody has an interest in contacting me regarding any of the work that I've done, I'll have my email address right up there, eric.garza@uvm.edu. So I think Allison wanted to moderate the Q&A.
Great. Thank you, Eric. All right. Is this on? Yeah.
It is.
All right. So now we're going to transition to a Q&A and discussion with our speakers. And Doug, you should feel free to come up here and join as well. Kate Blofson from the Office of Sustainability is going to be capturing some of the discussion on this flip chart here. And as we mentioned, one of the goals here is to capture some of the ideas, visions, questions that are coming up for us as a community around our campus food system. So if you have a thought or idea that isn't necessarily a direct question for today's speakers, you can write it down on these flip note, post-it notes here and stick it up on the board. And over the course of the semester and these seminars, we're going to be capturing that and sort of categorizing things and putting them together into some reports that summarize what we've learned here during these seminars. So, we're just going to open this up for questions now. I'm going to ask that people speak into the microphone. I know you can probably project, but we're capturing this on video today, so we want to make sure that we capture the feed from the mic and get all of the questions. So, who's got our first question?
I'm curious why the focus on ratios, which use division, rather than a net return, which would be a subtraction. The reason being, in this case, if inputs continue to climb and climb, that's not necessarily reflected by a ratio, whereas they would be if, similar to net returns, income minus expenses, for example, they would be.
I think the biggest reason I focused on that for this talk is because I wanted to limit the whole talk to 20-ish minutes. I definitely wouldn't say that the return on investment as a ratio would be the only thing we would want to be focusing on in a more detailed analysis. And it's definitely not the only thing I focus on when I'm chatting with the farmers that I work with. We talk about the net, we talk about the return. Yeah.
Eric, I was wondering if you could go back a couple of slides to the USDA data and talk a little bit about why I think it was dairy and grain were so agriculturally minimally intensive. Maybe some of this data could be unpacked a little bit for an explanation. It seems like those might be, I don't know, I guess my intuition would say that grain would be a little bit more agriculturally intensive, but I wonder if you could.
As far as the grain, being so relatively non-agriculturally intensive, it's the sort of thing that you prep the field, you plant it, and then some number of months later you harvest. It's all mechanical, it's all monocrops. So I would say that that's probably the biggest reason why grain is so unenergy intensive, whereas with fruits and vegetables, for instance, there's a lot more involved in tending that field than just the plant and the harvest. As far as why dairy is on the lower end, I think specifically, I really don't know. I mean, these are all emblematic of kind of ultra large scale industrial farms. So this is probably representative of a confined feedlot dairy. And in terms of why that's less energy intensive at a production stage than meat, I can't necessarily say. You?
No clue.
Okay.
I would have thought dairy would have been more energy intensive than that. Deb? Quick.
I just
Oh,
thought that
oh,
the dairy
microphone.
would involve some grass grazing. Not just grazing.
I think the dairy may include more than just these large ones. I mean, you got a lot of grazing, which is going to be less, I mean, it's one tier down on the food chain for their food.
Do you think that the pasture, maybe not 100% pasture-based operations, but the pasture or operations that use some grass are common enough still in the United States that would show up?
Yeah,
Okay.
you can see a lot of dairy cows grazing in California and Wisconsin and Vermont. So I think it's an element of it. And another thing to
Yeah.
think about is for grain, I think is you have a lot less application of pesticides than you do some of the other groups.
Yep.
Partly because the value of it on the other end is lower too. You don't want to exceed
Yeah.
your input. I mean, have more inputs than you can get
Yeah.
money out of it.
And
Part of that's a
grain-
price issue.
Yeah. And the other thing too, and this is kind of where the way that I'm reporting this comes in, is I'm reporting this as input calories over law suggested food calories. And grain, dried grain is a fairly calorie dense thing. It's not 100% starch, but it has a really high quantity of starch. And in terms of macronutrients go, starch isn't a particularly energy dense macronutrient, not as dense as fat, but you're talking 4 calories per gram. Whereas if you looked at, not a dry fruit and vegetable, but a as harvested fruit or vegetable, you're talking about something that's much, much less energy dense. It's mostly water, a lot of undigestible cellulose in that. And there's a good amount of sugar, but not the same density of sugar in a fruit or a vegetable as you would see the complex carbohydrates in grain. So that's the other thing to look at too, is you're ending up grain-wise with something that's it's a dried final product, and it's also something that, because it's so high in carbohydrate, is going to be fairly energy dense.
Eric, when you look at the data, can you separate out to organic or local from a conventional type agriculture that may use higher? Because I was just thinking in fruits and vegetables, I see with organic farms in this state, they do a lot of mechanical cultivation. They're using small tractors and they have to pass over it multiple times. So is there any granularity in the data to be able to separate that type of thing out?
So in terms of this USDA data, I can't. But it's interesting to look at these two vegetable farms. So we have a CSA vegetable farm, which is, in terms of its agricultural operation overall, so I'm going to go back one and look at fruit and vegetables. So at national scale, the agricultural segment of fruit and vegetables, this part right here, is about, I'm looking at an angle, but I'm guessing that's around 4 input calories for every loss-adjusted food calorie. Whereas when we look at this vegetable CSA, this is all agriculture because the consumers who pick up their CSA up on farm. So you can see that the energy intensity of their operation is about twice what the national average is for fruit and vegetables for the agricultural chunk of that. And then this vegetable CSA, all of these inputs are used on farm. Some of this fuel is used for deliveries, but most of it is used on farm. And then the labor and machinery and buildings are all on farm. So at 21.6 units of energy input, they're multiple times more energy intensive as a small local farm than the larger scale conventional. It doesn't have to be this way. I think it could be done a lot more efficiently, but I think a farmer has to decide that they're going to manage both for energy intensity and for production. And that can be a challenging thing for some farmers to do given how low their margins are.
I was just going to comment, Eric, and I appreciate all this good data for us to chew on, so to speak, that sometimes your small-scale organic farmers choose to cultivate multiple times, which is more energy intensive than using one spray regime.
Yep.
I would say. So they're, looking at the data, it's hard to compare you're not comparing apples to apples, I guess. And I'm wondering in the vegetable CSA, if you calculated the embodied energy in the fact that people were coming to the farm to pick up their produce rather than having it delivered.
I did not do that. When I was working with this particular farmer, we talked about the idea of giving a survey out to the CSA members to figure out, how far did they drive to come pick up their CSA, and trying to back calculate, the energy intensity, because they're driving out to come pick this up, and that energy is not counted against the farm. It's counted in that household energy use, and hopefully they're trip chaining, which means that they're coming out to pick up their CSA and they're doing a bunch of other useful things at the same time instead of just using that fuel to come out and pick up their CSA and going home. But yeah, I mean that's a hit that doesn't show up against the farm, but somebody pays for, someone uses that energy.
Thank you. And one other quick question before I think more about the seafood. And I'm wondering, is that farm-raised seafood, or are you looking at wild catch as well on that next one? Because it says agriculture, so I'm assuming that that's whatever they call it.
You could probably count that as more just producer, so that counts the fishing boats that go out in the ocean, as well as the agricultural operations that farm seafood. So it's a mix of both. I don't have off the top of my head statistics as to how much seafood is wild caught today versus how much is farmed, but.
Okay, yeah, I was just curious because in the latest Economist, there's a big article on seafood and the energy intensity of the industrial seafood, catch. Thank you.
Yep.
Hi, Eric. The next slide. See, I see pasture dairy there, and I see pasture meat. And I'm like, if you have pasture dairy, you also create meat.
Yep, you could.
So it's both. And the other thing is when you do maple sugaring, you're actually using wood from your woodlot. It's not like imported. So you're basically growing trees to do your woodlot. So then when you do pasture dairy, you're actually producing grass. So if you add the energy to your maple sugaring, you should add what the cows eat as energy on your pasturing. And you would.
Yeah, if the maple sugar operation did use wood from their woodlot, then I would treat it that way. But they don't. He uses something like 60 cords, and he has a small woodlot, but he'd never be able to support that amount of harvest year after year. So he buys in 60 cords of wood from a bunch of other people to supply his operation.
Okay.
They're great questions. I think Kaylin has one over here.
The transportation piece in one of the first slides looked pretty low, and I was wondering if the freight. And I was wondering if you could speak to the idea that floats around that local is a really energy savings in terms of transportation and whether or not that holds true.
I would say that it most decisively does not hold true, and the opposite is actually true. And I'm going to advance forward because I had another slide that I couldn't fit in, but that speaks to this directly. This is from a study that was done back in 2010 that looked at the amount of fuel, the number of gallons of fuel that are burned per ton of product moved based on 3 different shipping methods. And the semi-trailer, most of us have a sense of what a semi-trailer is. The mid-sized truck here is like a UPS or FedEx-sized truck. And then the pickup truck is obviously a pickup truck. So you can see that the energy intensity involved in moving a ton of product is going to vary tremendously as a function of how it's moved. And there are certainly some farms that do their deliveries with more of a mid-sized truck, but a lot of the folks that show up at farmers markets are moving their product with a pickup truck or a small van or something like that. So at that scale, you're seeing a pretty strong diseconomy of scale in terms of the energy that they're embodying in that product by moving it around. Yeah, so one of the things that I tried to work out for last fall's energy use and food systems class that I wasn't able to put together, but I'm going to see if I can get some of the food hubs to let me do an audit of their operation and see how energy intensive they are per unit of food moved, looking at food calories, to see if that aggregator function can deliver some of the economies of scale that, can make a local food system more competitive with, the national food system. Because you're right, people have this idea, and I run into this all the time in students who come into my energy and food systems class, think about this a lot, that the long distance transport of food adds a huge hit, energy-wise, to the total energy intensity of food, but that's simply not true. It's so small that it's almost negligible compared to all the other things. And the local side of it, moving things around in a pickup truck is really where the hit comes, if we become too reliant on that particular mode of distribution.
I think that's a great point that gets at some of our assumptions that we hold about local food and energy, and I think also the point that was raised about organic production and the amount of tillage and mechanical use of energy that it's required versus spraying gets to that point of, when you're measuring different values, some can sometimes be an interesting trade-off to look at. Well, we value, organic production on one hand because of the lower ecological footprint of it, and yet, we are seeing a trade-off with the energy intensity of it. So I think these are great points that are being raised. Deb has a question, and then we're going to go over there.
The output here is kilocalories, and in this country, we generally don't have there's no scarcity of kilocalories for most of us. So my question is whether there have been any efforts to do similar analyses, but with overlaying health indicators on top of these. So nutritional value of food rather than caloric value of food, which gets a little bit complex, but there are things that you could look at to get at a health value.
Mm-hmm. I am not aware of any, but I definitely agree that would be something that is both very complex and hard to do, but still very worthwhile. Yeah, because I've done some calculations looking at the vitamin A content of foods from certain farms relative to energy intensity, but I'm using vitamin A estimates from literature, for these different foods, and that bears, it's huge variability in terms of what the actual vitamin A content of different foods is on a farm based on soil quality and how things were raised and what varieties were used and all that kind of stuff. So very, very rough calculations is the best you can do on that front, unless you have a lot of money to do a lot of nutritional analyses of food, that's harvested from a very particular area. But yeah, I definitely agree that that'd be a very useful thing to do because, here in America we're notoriously, overfed but undernourished, whereas a lot of other countries it's a very different situation.
I just wanted to follow up on the earlier question. I find this information about transportation fascinating. And I was just, as you were talking, I just thought that the idea of comparing the different models of distribution the hub versus the CSA where everybody drives out to pick up their own versus maybe the city market or whatever different models. That would be just fascinating.
Yeah,
So I'm just cheering you on.
thanks.
As a follow-up to that slide, I wondered if you have seen or conducted any analyses of emissions of the trucks. Like, how does that correlate with the fuel used?
I would guess that it is a modest correlation, but certainly not a perfect correlation. Because with trucks, the emissions is going to depend on a whole suite of things. Size is one thing, but then the age of the truck, what kind of emissions controls are installed, that makes a huge difference, particularly for particulates. And one of my masters was in environmental chemistry, toxicology, and risk assessment, but the particulars of emissions, vehicle emissions, was not something that I specialized in. So, I think it'd be something that would be interesting to look at.
This question or comment came up a few questions ago, so it's a little out of context now, but just insofar as the assumptions that we make that sometimes aren't right, I work with livestock operations across the state, and one of the interesting things about the local meats movement that's assumed that it's more energy efficient is that as was mentioned over here before, livestock are very dependent on grass, and the growing season locally is very short for grass, and so having local meat production units requires some sort of harvesting of grass for winter feeding. And oftentimes we've done a couple of analyses, and that winter feeding cost really doesn't, or is far more expensive than the cost of transportation to bring products in from other areas. So just interesting how that can be counterintuitive.
Yeah. And the other side of the thing too, and this is something that I've noticed doing this analysis, is that if you're raising meat and you want to sell that at retail, you have to drive your animals out to slaughter and then to have them cut and packaged for retail sale. And the fuel component of driving an animal, driving a trailer load of animals out to a slaughterhouse that might be 2 or 3 or 5 hours away is pretty substantial. So for instance, the pastured lamb operation, a good chunk of their fuel use had nothing to do with what was going on farm. It was driving the animals back and forth, back out to slaughter and then dropping the carcasses off and then going back later and picking up the finished product. And then there's also the delivery component in there. This particular lamb operation sells mostly to restaurants, so they would then do a suite of deliveries. And then, of course, they do have a little bit of fuel used to make hay, but that's pretty much a minority on here. And the same thing is true with this pastured meat. A lot of this fuel use comes from the need to drive, the hogs out to slaughter and have them cut. And he happens to use a lot of tractor because he pastures the hogs, which means that he has to go back and prep the field and put some kind of a crop in there, a forage crop in there after the hogs are done in that section of it. So there's a lot of tractor use, even though he's operating kind of a pasture operation. It's not, hogs are really hard on land, and you don't just leave torn up land there over winter. You've got to cover it with something. And the dairy is, down here is a pasture dairy. So he does make hay on his land. He has a herd of about, for the year that this data is from, he had a herd of about 120 cows, 120 milking cows. So he had to make hay for all those cows, and he did buy in some hay. But you can see that that part of the operation is tiny, and he's just a commodity dairy operation. He sells he has his milk in a tank, and then Organic Valley comes out and picks the milk up, so he doesn't have to do any distribution. So that'll give you a little sense for how energy intensive the distribution side of some of these local operations can be, compared to just running a basic, pasture-based operation. It's that distribution side where a lot of these small farmers really end up taking the big hit. And that's something that I've been, interested in, chatting with the folks at the Center for Sustainable Ag, the pasture group, which is, they contracted me to do the dairy operation here, and they also contracted me to do the lamb operation. So that's something that we're becoming interested in, is how to separate out the distribution side of these operations, and then how do you work with the farmers to make their distribution side of things a little bit less energy intensive, along with finding whatever low-hanging fruit you can with the farm itself.
Any other questions right now?
It's less a question and more food for thought. But when you go back to your slides where you see the energy per unit of food go up over time, like the historic timeline, like that one, can we put points in there and say, how was the food distributed, say, in 1910? Typically, how was the food distributed in 1940? And, like in 1920, people weren't driving cars around so much. When I grew up in the 1960s, it's like we had a milkman with a little electric car bringing the milk door to door. And that was pretty much for all the food items. So there is a whole history. As we got more energy available, we started using it more in distributing the food. Like as we could, we did. That's
Yep.
kind of.
And yeah, and the distribution side of things is interesting to think about in the context of this graph, because here we are, I think this last piece of data is 2007, but here we are in 2014, and the energy cost of long distance distribution of freight is just a tiny, tiny sliver of this whole area underneath this curve. But how has that changed over time? And I don't have necessarily the data that allows me to break that down for all of these different years, but that would be, if you had a way to do that, if you had a way to look into the past and get a reasonably accurate assessment of that, I think that'd be interesting to look at. Some of those older models of distribution might serve as interesting inspiration as we try to figure out how to make a local food system that works. Acknowledging, of course, that the infrastructure that they had back then is completely different than the infrastructure that we have now. So it's not going to be a perfect correlate necessarily.
I think this graph in particular would be one where it'd be very interesting to see a net return in addition to a ratio, because I think over this period of time, yes, our energy consumption has increased exponentially, but food production has probably followed an even steeper climb, I would guess, and it would be very interesting to see that net return over this period of time. Do you have any thoughts or senses on how that would have changed over this 120 years?
Well, sure. I mean, this is inputs divided by outputs. So if instead you wanted to take outputs minus inputs, well, you'd have to, yeah. If you did outputs minus inputs, the result would be negative, because the inputs all along this graph are much, much bigger than the inputs, or the inputs are much, much bigger than the outputs. They're a little bit bigger way back here, and then they're a whole lot bigger up here, where the inputs are, just looking at the data that they're talking about here, they're on the order of about 14 units of input for every unit of output. So the net here would be about 13. The net here would be something like 12-ish, 11-ish. And then, you could fill in the blanks back here too. So this is probably around 13. So the net would be about 12. And then down here, the net would be like 0.2 or 3. So I think in this case, looking at net rather than a ratio isn't going to radically change what this graph looks like. You're just shifting it down by 1 unit, basically, because it's normalized per 1 unit of loss-adjusted food as a kilocalorie.
Eric, I'm just thinking off the top of my head here about the household level and the type of consumer we have at the household. Some consumers are buying whole foods, so to speak, and processing them in their home. And other consumers are buying radically processed, value-added foodstuffs. And I'm wondering if you could look at those different consumers, you know, some sample size, and think about the energy that it takes to process that food at either a processing plant or at the household level, and whether we might be able to have some influence on this whole chart here. I don't know, I'm just thinking, you know, the household level is where food is consumed, and that's where a lot of that energy happens, but also at the processing level or
Yep.
scale.
Yeah, so in general, and students from my energy use and food systems class can attest to this because I had them do some of these calculations as part of their homework assignments. In general, when you do larger batches of cooking, it's more energy efficient per unit of calorie that you end up with. So if you have a large processor do the work, you're probably investing less energy per calorie of food that's going to eventually be eaten than you would if you had a household consumer buy that same thing and make and cook like a single serving. So I guess that this is another area where you end up with a trade-off, whereas buying the whole food and investing the extra energy to prepare it and process it yourself is probably going to yield a more healthful product. And so there's this trade-off between the ultimate goal of producing a healthy health and well-being from food versus minimizing the energy that gets invested. Because certainly we could all, we could probably cut a certain amount of energy off of this column if we all ate processed foods and just microwaved everything in our bought stuff that was freeze dried and all you had to do was rehydrate it and then put it in the microwave for a minute. But is that really a step in the right direction?
We have time for one more question.
I'll just follow up on that question because I'm feeling a little bit guilty about driving to raspberry patches and canning. But have you looked at homesteaders or backyard chickens is hugely popular now. And as we built our chicken coop in this summer, I thought, wow, well, this is a lot of materials for 12 chickens. And I go to the store and get 50 pounds of grain at a time. And so we see this as popular, we see this as sustainable, at least I do, and I think a lot of other people share that. And so have analyses been done on that front? As I look at the graph that starts in 1920, I think, well, there's probably much less waste then. People were probably canning more. They were doing some of these same things. There was backyard flocks and people had a family milk or cow, and we're starting to go back to that. So how does that affect the
That's
equation?
a wonderful question, and I would love to do some of those analyses, and just kind of looking. I've got a number of friends who have like backyard chickens and things like that too, and sometimes you're right. There's a lot of invested materials per chicken. Yeah, but I haven't done that yet, and so I don't know which direction that would go. It might turn out to be shockingly efficient, or it might turn out to be shockingly inefficient in terms of a return on invested. And it also depends on what sort of a product we want to get. If we just want poultry, the meat, that's generally more energy intensive because you're taking the animal out of production. If all you're interested in eggs is you're investing in something and it's yielding a small return over time. So it's a different, depending on what kind of a product, people are going for with that sort of an operation. I think that'll have an influence on what kind of a return they get. And that actually, now that I think about it, is maybe part of the reason why meat and dairy are so different. Because with dairy, you're investing in this animal, and then the animal can yield a caloric return without having to die. Whereas with meat, you're investing in this animal and then you kill the animal and then you have the meat. So in that regard, I can see how, having the family cow would be a good return on investment as long as you can tolerate the milk. And eggs might be a similar thing. But yeah, short answer is I haven't seen any of those analyses done, but I would be really interested in doing some of those. So if anybody has a backyard chicken operation or a milking cow, give me an email and we'll see if we can do an audit and get a sense for what the return on investment of that is. I think that'd be interesting to look at.
I'm going to take advantage of the last 2 minutes here to pose a philosophical question for Eric and Doug both. So as we think about the energy intensity of our food system, a lot of what we're talking about is production and processing, transportation outside the borders of an institution like UVM. So as we think about our campus sustainability, what role do you think we have as an educational with an educational mission, an institution of higher education, in terms of thinking about these things as we make food purchases?
Well, I'll take one stab. Number one, you support people like Eric and others doing this kind of research so that you actually are looking at data, not anecdotal feelings about what is good or bad. And so looking at this kind of data and doing that kind of research, I think is just very informative. Then I think it steps to the next level. What are our values? And that, different people have different value sets. For some, it's critically important that what are the costs, what are the hidden costs in the ecological damage that may be occurring under one set of circumstances versus under a different set of circumstances? What is that value over time? What is the long-term consequence that we'll pay for? And I grew up in the era when Lake Erie caught on fire, although that's kind of a misnomer, but our solution to pollution was dilution until we couldn't dilute it anymore, and then we had a problem. But up to that point, we didn't think it was a problem. And so it's those long-term, what do the economists call them? Externalities. We tend to forget about the negatives that we create when we create a system, because they're external to what we're trying to generate. And so we don't do a very good job of incorporating those costs that we create that someone else in the future is going to have to pay for. So I think it's that values, it's the economics, it's the data to find out exactly what, and then putting those pieces together. And as an educational institution, I think that's our role, is to try to put all those pieces together and stimulate that debate, and then try to employ something on a campus that tries to balance or compare or contrast a range of things that are going on in society to show a potential new direction. I work in extension a lot. I'm the director of extension here in the state. So you want to bring good ideas, but in the end, individuals have to make their own decisions about what they implement and what they don't implement. And so I think this is an opportunity for an academic institution to do that as well.
Yeah, I think that's a good way of looking at it. I guess from my perspective, I think it's really important for an academic institution to be very transparent about its goals and its values in the context of its food system, and then to try to use some of its coursework that students undertake as a way of giving students a firsthand experience, looking at some of the data and figuring out the numbers and really just learning how to approach questions like this through a transparent analytical lens. Because that's one of the things the sense that I have is that a lot of the students who've taken my energy use and food systems class, I think that's one of the things that they really appreciated about it, is I make them do math, which they really hate, but in the end, they sit down and they end up doing an energy audit of a farm, and they get to crunch all the numbers, and then they come out with this number at the end, and then it's almost as if a light bulb is going on. It's like, wow, I never really understood what all these impacts really were until I sit down and I do it. So I think a huge part of the university's opportunity, at least, is to ask some of these hard questions, but also create avenues for the students to be involved in coming up with the answers and using this process of inquiry as a way to develop students professionally.